All right, so you've probably all seen this plot. This is the number of sequences in GenBank per year, and it's current as of 2014. And this volume of data is growing exponentially. This has been talked about. And it poses several problems. One problem is computing on the data. Another problem is storing it. Another problem is transmitting it. It's tempting to think that cloud computing can solve this problem, and it can save some money and provide flexibility. But the problem is that it doesn't address the fundamental issue, which is that cloud computing is still constrained by Moore's law. And if you want to take advantage of cloud computing, you have to transmit the data up to Amazon or wherever, and it helps to be able to compress the data in an efficient way. Now, this is the same data, but on a log scale. And this is the growth of computing power according to the top 500 supercomputers list. And this is the growth of GenBank. So they're on different exponents. This is kind of a problem. Well, one thing we can do to help with this is to take advantage of redundancy in data. And this is where compression is going to come in. Now, this is just a little cartoon showing the sizes of several fruit fly genomes. And here we've taken simulins and Drosophila seychellia and removed what's redundant between them. And the black bar is, so the yellow bar is the size of Seychellia's genome. The red bar is the size of simulin's genome. If we combine them and show only what's unique among the two, we get the black bar, which is only a little bigger than Seychellia. And if we go a little further and bring in Drosophila melanogaster, well, the unique data is a little bigger, but still, we're doing better. Even when we bring in much more distantly related species, we see that the unique data is relatively small compared to the concatenated set of all the genomes. All right, so maybe compression is useful in looking at genomic data. So this talk is going to basically comprise 3 parts. First, I'm going to give a little bit of general background on compression. Most of this stuff is more than 20 years old. Some of it's a lot older than that. Talk about compression in terms of storage and transmission for genomic data. And then talk about what we call compressive genomics, which is how you can take advantage of compression not just to save space, but also to save time. I'll note that storage and transmission have very similar requirements. In other words, if you zip a file, it saves space on disk and it's less to send over the network. But there are some important differences. For example, if you're transmitting data over the network, it's nice to be able to do things as it streams and not have to wait until the whole file's downloaded to be able to work on it. All right, so jumping right in. Forgive me, I got a little bit of a cough as well. So Shannon in 1948 demonstrated a fundamental lower bound on the size of a data set if you don't want to lose data. Or you could think of this as a fundamental upper bound on how good a compression ratio can be. So if we have n random variables from some source, and each of those variables has a given entropy, h of x, which is, this is just Shannon entropy. It's the number of, it's basically a measure of the surprisal of an observation. How different is it from all the other observations coming from that source? If we have n of those, they cannot be compressed into fewer than n h of x bits without loss of information. Right, so this sets a bound on how many bits are needed to compress any data source, measured in terms of this, unless we are willing to throw away information. So what can we do if we want better compression? Well, one thing we can do is try to approach that Shannon limit as efficiently as possible. We want compression to be fast. We want decompression to be fast. That's often more important. And maybe we can leverage some tricks to get closer to that limit more efficiently. The other thing we might consider is being willing to throw away information. All right, we're all familiar with JPEG or MPEG compression for photos and music and video. That's what this is doing. It's throwing away the information that we don't think is going to matter in the end. So how might we approach the Shannon limit? Well, I'm going to talk about 4 approaches that are not new, but are kind of fundamental in that a lot of the other things I'm going to present build on them. All right. So Huffman coding gives us a variable length prefix code so that the more frequent symbols, the observations we see more often, take fewer bits to represent. So let's think about DNA, right? We've got 4 bases, A, C, T, and G. And, well, if we want to be really naive, we could use a full byte to store each one. This is what a FASTA file does. This isn't really a good idea. We can be slightly more clever and realize that we only need 2 bits per symbol to represent this alphabet. This is ignoring things like ends for no call and so on. Now, where this gets interesting is suppose we have some real bias. It turns out that Plasmodium falciparum, which is one of the malaria parasites, has only 20% GC content, which is kind of wild. It's 80% AT. So what would happen if we built a Huffman code for a genomic sequence of falciparum? Well, we've got our 4 bases, and we're going to list the frequency of each base. I'm saying if it's 80% AT, then it's, for simplicity's sake, it's going to be 40% A, 40% T, 10% C, 10% G. And then what we do is we take the 2 least frequent of these leaves, and we're going to build a binary tree. So we're going to join those 2, and the combined frequency is 0.2. And then we're going to take the next least frequent. Now we're breaking ties arbitrarily here, but let's just take T, bring it into our binary tree. We've got a combined frequency of 0.6. And then finally our A, and that fills out the probability. And then what we're going to do is label this. We're going to start out here, and we're going to call it 0. And if this is 0, then the whole rest of the tree is 1. And then we're going to go down this tree a ways and append a 0 on this side and a 1 on that side. And we're going to append a 0 here and a 1 here. And the important thing about this is essential, is that no symbol here is a prefix of any other. Now, I'm not counting the intermediary ones here, but 111, 110, 10, and 0 have no common prefixes. No, I should say no one of them is a prefix of another, which means we can take a sequence of them and uniquely decode them. There's no ambiguity. Well, what does this give us? Well, the naive encoding was 2 bits per base. The Huffman coding turns out, if we look at the frequency and the number of bits in the code word, well, A occurs 40% of the time but only requires 1 bit. Turns out we get to a net of 1.8 bits per base. So this is a small savings, but this is also a pretty trivial example. And you might actually have uneven bias if you were talking about compressing a long set of transcripts, rather than here assuming that we've got 2 strands, and so A and T have the same frequency, and so on. All right, so this is Huffman coding. You build a prefix tree and use non-prefix code words to represent symbols, and the smallest code words are given to the most frequent symbols. So in expectation, we'll use very small code words a lot of the time. Another old technique And I'm covering these because they are essential to many of the state-of-the-art compressors, right? These are really tools that are still being built upon. So arithmetic coding encodes an entire message as some number, some high-precision number. And the way it does this is it divides up the number line between 0 and 1. So here we've got our same, for the sake of simplicity, our same frequencies. And if we want to divide up the number line between 0 and 1, we're going to put A in the range, the half-open interval 0 to 0.4, T in the half-open interval 0.4 to 0.8, G 0.8 to 0.9, and C 0.9 to 1. And then how could we actually use this? Well, it's essentially a recursive algorithm. Let's take everybody's favorite short nucleotide string, Gattaca, and see how we'd encode it. Well, we start with G. I hope you guys can read these numbers. It doesn't really matter. So G falls in the range 0.8 to 0.9. All right. So we're going to start there and expand that range, essentially map that range back to the whole interval again, and say that, well, now for our second letter, A is going to be in the range 0.8 to 0.84, T from 0.84 to 0.88, G from 0.88 to 0.89, and C from 0.89 to 0.9. So this whole range fits within this little window. And we're going to, since the second letter is A, choose A, and we're going to recurse, do the same thing. And now our new window is 0.8 to 0.84. T is going to fall in this window. Same thing. We just get to more and more decimal places. And finally, we end and say, well, we're at the, there we go. We're at the, might as well represent the beginning of this interval. The last letter is the A, so 0.824704 stores this message. Well, the neat thing is now we've got a uniquely decodable number that represents our string. There are a few problems. First is, how do we know when the message ends? And the answer to that is, I lied, we need a stop symbol. But I didn't want to complicate the picture. We either need a stop symbol or we can only store fixed length messages. The other problem, especially for those of you who know something about computer architecture, is that floating point precision rapidly breaks this for any reasonable length of message, and or the fact that floating point numbers are imprecise. So there is an integer version of this which has some magic rules, is a little unsatisfying, but it's been used for years. More recently, Rodionov and Volkov came out with a treatment using p-adic arithmetic, which is really cool. I'm not going to get into it here, but it basically solves this this sort of unsatisfying problem. The magic rules go away, and it turns out there's a nice fixed precision treatment to this. So look it up if you're interested. And another interesting little aside is that Huffman coding turns out to be a specialized case of this. It's less likely to be optimal in the sense of reaching that Shannon limit. Okay, another technique that we're going to see show up is
which one is less likely? Huffman?
Huffman coding is less likely to reach the to approach the Shannon limit, or it's not going to get as close to the Shannon limit as a good implementation of arithmetic coding. Another thing that can be done with arithmetic coding, I should mention, is that that frequency table could be changed. It can be adaptive. So it doesn't need to be a predetermined frequency table that's fixed for the whole message.
Can I ask you a question?
Yeah.
Because I don't know this perfectly, but I thought that Shannon encoding was in fact optimal.
Shannon, no, Huffman coding.
Huffman encoding was in fact optimal. Therefore, it must be as close to the Shannon limit as anything.
It's really not. In fact, the closest, there was work in the 90s, Gallagher codes reached closer to the Shannon limit than had previously been done. Mind you, Huffman codes are much older.
So then can you say, what is Huffman code optimal for? Because we all learn it's optimal.
It's
if it's truly, yeah, if it's truly IID, but it's not always going to pick out.
It's not uniform, but okay.
And also if
Yeah.
it's like distributed as 2 to the 1 over 2 to the power of x, then it's
I know,
exactly.
yeah, I know that theorem too, but I thought just algorithmically, whatever your distribution is, that's what
It's for prefix
Huffman
codes.
coding does for you
Among the prefix codes,
among the prefixes.
then it's so.
Okay.
Say is that if you code over longer blocks, now you're only considering
Oh, okay.
ATGC. If you want to take longer blocks, then it's really.
So, okay, so the proper statement is that Huffman coding is optimal among the prefix codes. Good.
Yeah. Okay. So next, I want to briefly mention Lempel-Ziv. I wasn't here yesterday. I gather Dan Gussman may have already talked about it. But basically, so I'll be brief here, as I will with Burrows-Wheeler. The idea is to slide a fixed length window along a sequence and replace already seen patterns up to some maximum length, and this is its big limitation. And so, we've got our string again, slightly modified, so we have a little ringer of redundancy in here. And we slide a window along, and as soon as we hit something that we've seen before, we can replace it with a pointer to where we saw it. Well, it's at position 1 if this is 0 indexed, and the length from there that occurs here. Limitations of this are that we typically want this tuple to be stored in a machine word, maybe 32 bits, maybe 64 bits. And so there's a trade-off between the size of the pointer and the length that we can efficiently store. So maybe we want to be able to jump really far back in sequence. That bounds how much of a repeated sequence we can store right away. But this is efficient. It's used in gzip, zip, PNG compression, many other areas. And yes, indeed, there's the pointer and the length. Burrows-Wheeler Transform, I think, has been talked about enough here, so I'm only going to say that it is block sorting compression. It is not itself a compressor. It's a way to sort input reversibly in efficient space, such that it lends itself to run length encoding. Right? What we get is a lexicographically sorted string that we know how to unscramble back into what it came from. And because it's lexicographically sorted, it can be run length encoded very efficiently. Okay. So now I want to get into genomic compressors. So we want to get close to the Shannon limit efficiently. Why not just use a general purpose compressor? In other words, why not just take fast-A files or fast-Q files and run gzip? And this is actually done, right? BAM files are essentially, so BAM uses a nice little library called BZGF. It's a blocked gzip, and that solves the random access problem. We can now seek to some location within our big compressed file and only uncompress a small part of it. But really, there are different kinds of data we're interested in compressing. There's sequence data, and there are also quality scores if we're talking about next-gen sequencing read data. And there's one quality score per base. And when we're talking about how much uncompressed space these require, or how much compressed space, our sequence is only a 4-letter alphabet, but our quality scores, if we're talking about Phred scores from Illumina, are until recently a 40-value range. So there's a higher dynamic range here. There's more information content per position, so it's going to require more space. The other thing is that, with maybe a few exceptions, I think we want our compression of sequence to be lossless. There might be cases where we're OK with approximate, some amount of loss. But generally speaking, sequence compression should be lossless. Quality score compression, lossy compression might be OK. We might be OK with throwing away some amount of data. And I'm going to get to that a little later. The other way to think about this is, can we pre-process the data in some way that general purpose compressors can do a better job than if we naively gzipped our FASTQ file? So we want to try to take advantage of structure. Now, one way to do this is to store differences from a reference. If we've got a reference genome for whatever we're sequencing, even though Lior said we should never align to that reference, if we do, we can compress by storing only the differences from it. The other option is, if we don't have a reference, we can still cluster similarities among reads. I'm going to talk about a few ways that this is done. That's important when we don't have references because we don't have references for every species. Right? We don't always have reference data for what we're sequencing. So the very first technique I want to talk about is called SCALCE. And I apologize if I butcher it all, because this comes out of Cenk's lab. This is a reference-free compressor that uses something called a locally consistent encoding, which I will try to explain. What it does is end up bucketing reads by substrings, and this improves both the runtime and compression of a modified LZ Lempel-Ziv compressor that's run on the result. So in other words, here we're going to notice a pattern in the data, and rearrange the data in such a way that a general purpose compressor does a better job of it. So, all right, here's the locally consistent encoding algorithm. First, I'll just tell you the steps and then show you a short example. We're going to identify local maxima in a sequence. And what do I mean by that? We're going to impose some lexicographical ordering, right? A, C, G, and T, we can turn them into 0, 1, 2, 3. And 3 will always be a local maximum. 0 will always be a local minimum. So we're going to identify local maxima. Then we're going to identify any local minima that aren't next to a maximum. We're going to partition the string based on those. And we're going to extend those partitions left and right to come up with blocks. And these blocks are going to be useful. Now, I'm going to show a non-general case of this. The paper has an explanation of the more general case that only handles strings of the form XOX, where this doesn't actually have to be 0, but it doesn't handle tandem repeats. Turns out the more general version does. So let's take a string that happens to fit this pattern. And so it's got a 0 in the middle. I just colored it red so you'd see it's the thing in the middle. And I've bolded. Turns out there are no local minima here that are not next to a local maximum. So it's all local maxima. I've bolded them. Now, then we partition on each side of each maximum and on the ends. So we're just breaking this up. And extending left and right, we get these overlapping blocks. Now, what's interesting about this is only that aside from the margins, we get the same core blocks from both sides of this, right? Just by following this rule of looking for local maxima, we get 3120 here, and we get it here. We get 2032, we get 2032, and so on. So here we've got a nice little heuristic that gives us consistent partition or consistent core blocks from a long string. Given that, and I mentioned the real implementation is more complex. In the real implementation, core blocks are between 8 and 20 bases, and it turns out that in the experiments shown in the paper, 99% of all high-throughput sequencing reads of length greater than 50 include at least one core of length less than or equal to 14. Right? So these things empirically are good at pulling out consistent blocks. Then you just identify overlapping reads by these core blocks and reorder them, and LZ77 does a better job than it otherwise would. So the next, and I'm not focusing on the specific results for each of these because I want the flavor of this to be about the algorithmic techniques. All of these papers were chosen because they have excellent results, not because their authors are here. That's a coincidence. All right, so DZ is another compressor, and this one is reference-based. So it relies on having some mapping between reads among reads to a reference. And the idea is to partition these reads into blocks, build a contig that covers all the reads within a block, and encode just the locus for each read within the contig. So the idea is that most differences between reads in a reference should be shared by nearly all the reads that map to that locus in the reference. In other words, other than sequencing errors or highly allelic regions, all the reads that map to a given locus should agree with one another. And we can store the few cases where they don't by encoding those rare differences. So a little picture of this. So we've got a reference here. This is exactly the same example as in the paper. And we've got several reads that map to this reference. Now, here we see that all of these reads disagree with the reference in this position. So this is unlikely to be a sequencing error. It's probably a SNP. Here we've got, again, a case where they all disagree. This is likely to be a deletion. And here we've got one of them disagreeing. This is more likely to be an error. Well, we can store this as the new consensus sequence based on these reads. So now we've put this C here and a gap here. And we would also store out of band this one difference. This is lossless compression. We don't want to ignore that potential sequencing error or potential allelic difference. So we'd store this. And these can all be reconstructed from this and this out-of-band piece of information. DZ has a few other tricks up its sleeve. It tokenizes the read names in a SAM file. Those actually occupy a fair amount of space. As I said, it uses LZ77. It also does, and I'm going to cover this later, lossy quality score compression, just as SCALCE does. And importantly, it provides random access. So, and I'm going to come back to the quality score compression in a few minutes. All right, another sequence compressor is PathEnc. And Carl Kingsford is also here. So PathEnc is reference-based, but it does not actually do alignment to the reference. And it relies on a statistical generative model of reads. Now, PathEnc is a little different in that it was demonstrated on RNA-seq data. There's nothing about it that actually makes it inappropriate for DNA. So I'm just going to walk through a little example of how it works. We're going to use a RNA alphabet here. So we're going to again slide a little k-mer window along our sequence. And we're going to build a graph where each k-mer, there's an edge between any k-mer and the k-mer that immediately precedes it. Okay? So initially this looks very trivial. As we slide this window along, we're going to build up a path. But we've seen this guy before. It's already here. There's supposed to be an edge going back. And now there would be an edge from here to here. So basically we get some path in a graph that allows us to recover our read. And there's one node per k-mer in that graph. And there's an edge between k-mers if they are sequential. So, all right, so each read is encoded as a path. And they're encoded in two different streams. The first node of each read path, which is called the read head, is stored in one stream. We build a 4-array tree, 4 for the 4 letters of the alphabet, of depth k. And we can just traverse that tree in a fixed order, emitting a 1 for any edge that's actually present. So we've got a bit stream, a 1 and a 0 if the edge is not present. So we get a bit stream that comes from this tree of present k-mers. And so we can gzip that resulting bit string. But because the traversal order of that tree is predetermined, we can recover the entire tree and thus recover all the reads from the compressed bit string. Or recover the heads of each read. And then the remaining nodes in the tree, the read tails, are compressed using an arithmetic coding. Now, I mentioned one advantage of an arithmetic coding is that it can have an adaptive probability distribution, right? We don't assume that the emission probabilities of each nucleotide are the same through a whole genome. In fact, they can differ significantly. Here, each node in the graph gets its own probability distribution. So they're redetermined. Now, something interesting here that I'm going to come back to is that for PathEnc, they found that so it probably can't read the numbers, but here the y-axis is size as a fraction of 2-bit encoding. So lower is better here. And the x-axis is length of k-mers. These are two different read sets. Here, k-mers of 16, so 16 mers give the best compression. So that's what they used. I'm going to come back to that a little later after I talk about some quality score compression. I also want to talk about MINCE, which is another compressor from Carl's lab. This one is reference-free, and I'm going to go through it kind of quickly, but it basically buckets reads based on, again, short k-mers, 15 mers. And the idea is that it replaces a common k-mer with a pointer and reorders the reads within each of these buckets. I'll show you what this ends up doing. But this, again, ends up boosting LZIP and gzip performance. So here we've got some read, And this doesn't even show up on here. But we've got a common bucket label, which is AGCCA. All right, so this guy here is our label. Because everything that goes into the same bucket has this same label common to it, this is stored out of band. It's just a pointer to it. And, well, there isn't even a pointer. There is an offset where this occurred in the string. And then this is flipped, so it's stored with the suffix of the bucket label at the beginning and the prefix at the end, along with the offset of the bucket label. And basically, the idea is that the compressor should be able to take advantage of the fact that these all follow the bucket label and basically get better locality of the reads within a given bucket. So this again provides excellent compression and runtime performance. This transformation is called split swap read transformation. Yeah.
How are the bucket labels chosen? Are they chosen to be something that's common in the sequence?
So they're chosen. I didn't go into the algorithm. It's covered well in the paper, but basically, so ties are broken according to lexicographic ordering. So we're going to choose early, smaller buckets first. But basically, they are the most common Elmers, where L is, I believe, 8, in a given. So it's the most common Elmer in a read, and if that or in a k-mer, and if that's been seen before, it's mapped to the same bucket, and if it's not been seen before, then it becomes a new bucket. All right, so this is what I wanted to cover for sequence compression. And I now want to switch gears slightly and talk about the quality score problem, because, as I said, this is a bigger problem. So, all right. So modern sequencing equipment is not perfect and introduces errors. Fall off that. So sequencing equipment gives quality scores, which are a measure of the confidence in the base call at each position. Now, the problem is, as I said, these take more space, in fact, than the nucleotides if we compress them naively. So given reads from a genome, can we efficiently compress quality scores without losing too much accuracy? In fact, we might even improve accuracy. So the role of quality scores in SNP-calling is we've got some raw reads in a FASTQ file. We're going to, apologies, Lior, map them to the reference and use something like GATK or SAM tools to do variant calling. Now, in a compressed workflow, we might substitute. So if we've done a lossy compression of the quality scores, we can't recover the originals. So now we've got an alternate pipeline where we have some new quality scores, and we're going to feed them into the rest of this pipeline. So, as I mentioned, there's a greater dynamic range than sequence data. A compressor could be lossless or lossy. I'm going to focus here on a couple of lossy implementations. So the first, and this is actually relatively recent, although I think there's more sophisticated work that's been done earlier. Illumina has started, and they turned this on recently by default to support their cloud platform, collapsing the dynamic range from 40 to 8. They call this 8 binning. They've demonstrated a small effect on SNP calling error, and it's available in CRAM. But basically, they said, well, we're going to take a no call, and it's still a no call. We're going to map 2 to 9 to 6, 10 to 19 to 15, and so on. And there is a white paper on this. If you are curious, it's worth a look. But I want to talk about a couple of approaches that are, I think, a little more interesting. So SCALCE also includes lossy compression quality scores. And the observation here is that neighboring quality scores are often similar. And this observation is also going to be true in something else I'm going to talk about. And the idea is reduce the dynamic range, apply arithmetic coding, and we get a small loss of SNP calling accuracy as a result. So this is part of the, I'm not going into great detail here because it's part of the SCALCE paper I already talked about. There's also QVZ from Malcia et al. The two of the co-authors on this paper are also here. So I'm again talking about somebody else's work who's present. Here the key insight was the realization also that neighboring quality scores are likely to be correlated. Not necessarily similar, but correlated. The work is based on rate distortion theory. The idea is to discard as little information as possible for a desired bit rate, and let's see, the approach is basically compute the transition probabilities for a first-order Markov model. So walk along our quality scores and look at how likely a given score is based on its predecessor. Construct a code book using the Lloyd-Max algorithm, which I am not going to cover. It's explained pretty well in their paper. And quantize the input using that code book and use, again, an arithmetic coder. So the thing I want to go into only slightly here is, here's how the quantization works. We've got a bunch of values, and we've got these B's are the bin boundaries, right? We're going to say that anything in this range, B0 to B1, gets mapped to the same value. Anything in this range, B1 to B2, gets mapped to the same value, and so on. However, when it's decompressed and the value is recovered, it's not just mapped to the midpoint of this interval, which would be commonly done. It's mapped to a point in that interval that minimizes the distortion of the original signal. So hopefully that's a slightly fair covering of it. So QVZ also shows significant compression with minimal loss of, or even no loss of, downstream SNP calling accuracy. And finally, for this section, I want to talk about work that came out of our group called Quartz. So what Quartz does is it compresses quality scores by smoothing many of them to kind of a unit value. So first, what Quartz does is it does rely on a reference, but it does not need to be a fully assembled reference. It relies on a corpus of reads from which you generate a dictionary of common k-mers. And this only needs to be done once, typically per species. So then, compression works. So we've got our sequence and our quality scores, and we've got some reads. So we're going to break, so this is a read. We're going to break this read into k-mers. And these are 30 tumors staggered every 16. So they're half overlapping 30 tumors. And I'll talk about, I mentioned the 15 mers from Carl's work earlier. I'm going to talk about 30 tumors a little bit and why there's this difference here. What we want to do is find all Hamming neighbors within a Hamming distance of 1, so all immediate neighbors. And the reason, I'll get into why we use only Hamming distance of 1 in a minute. And we want to be able to quickly identify neighbors in a neighborhood of the query, so we implement a deterministic data structure that makes that neighbor query very efficient. Now, we note where there's a difference between the read and what we find in the k-mer dictionary, and we store the quality value for. So if we see a difference in a Hamming 1 neighbor, that is, we consider that likely that it's either an important error or it's a real variation. So that quality value is stored. And for all other positions, so here we found a difference. For all other positions, they're simply smoothed to a uniform value. And the basic idea is that anything where we have a Hamming 1 neighbor of the read in our corpus, so from this species, that quality value is likely to be important. It either tells us with high confidence that it's a real variation, or with low confidence that it might be an error, but in either case we want to let the downstream pipeline use it. But all of the rest, we're sort of saying that there isn't a meaningful difference between the values represented here. They all agree with the reference, and if they were low values that agreed with the reference, you know, it's possible that that's a variation that we're not seeing, but we don't know what the variant would have been. So there's little point in storing it. We can't do a positive variant call from that. So one of the challenges here is that we need to quickly find all 3K Hamming neighbors of each k-mer. Why 3K? Because at each position of our k-mer, we've got some base. There are 3 other possibilities. So there are 3K Hamming neighbors, that is, other k-mers with only a Hamming distance of 1 away. Naive approaches to this would include a sorted list, which is memory efficient, but CPU and cache inefficient, or a hash table, which might be faster, but it's memory and cache inefficient. So we use this locally sensitive hashing approach, and I'm gonna gloss over this, except to say that we project each k-mer onto a random k/2mer, so half the length, forming a family of hash functions. And there are two orthogonal ways we can break this, we can do this projection. So I'll show you the picture. We basically have our dictionary, and we can cluster by the front half of the k-mer, and that's one set of hash functions. We cluster by the back half of the k-mer. That's the orthogonal projection. It's another set of hash functions. And we can very quickly do a lookup for a k-mer within this to see if it's present within this table. And so I don't want to focus on results here, but Quartz does. The downside is Quartz consumes a lot of RAM. So it is not something easily run on a laptop. But on the other hand, it gets down to only 0.35 bits per quality score. It's very fast. And the very surprising thing is that Quartz doesn't just not significantly harm downstream base calling accuracy. It actually slightly improved it on some test cases under the metric of area under the ROC curve. Now, a caveat to that is that if the improvements are all out here on the ROC curve, and we really care about this area, it might not be a significant difference. But the reason this is a little surprising is that when we talk about lossy compression, one of the goals is to try to be able to recover the original signal as closely as possible. And here we're throwing away a lot of the original signal. But the original signal we care about is not the quality scores at all, right? Those are artificial. Those are a measure of what the sequencing machine has done and where it's screwed up. What we care about is the underlying sequence. And if the quality scores are misleading with regard to that sequence or just carry additional noise along, then they're carrying no useful information. So if we can remove bits that are used there and use those bits for the quality scores that give us that actually carry information, then we expect to be able to do at least as well. So I guess sort of a meta lesson here is that the real signal we care about is not quality scores at all. It's the underlying sequence. I mentioned this difference in k-mers. This is sort of peripherally relevant to compression, but I wanted to go over this. So MINCE found that 15 mers were optimal for its implementation, for its case, with 8-mer labels. And this makes sense because the labels are being used as almost as a seed for search. You don't want there to be too many of them. Quartz found 32 mers were optimal, and that's because they're being used in a different way. They're being used to look for Hamming 1 neighbors. So if we think about a given genome, it's not unlikely that all possible 8-mers may exist. If we go even smaller, we expect that all 4-mers probably exist in a given genome. But most 32-mers may not. And when they do, they tend to be unique or almost unique, with the exception of tandem repeats and low complexity regions and so on. In fact, for the human genome, with k equal to 16, the k-mer, a 16-mer is only unique 21.8% of the time. And at Hamming distance 1, it's almost never unique. 32-mer is unique 85.7% of the time. And at a Hamming distance of 1, it's still unique almost 80% of the time. So this is, I think, an interesting result. The lesson to be drawn from this, I think, is that size of k-mers matters in multiple ways, in terms of efficiency and in terms of what question you're using them to ask. Another picture of this is x-axis is k-mer length, 32 here, 16 here. And here's the number of loci identified for, this is just the total number of unambiguous loci and the number of unambiguous loci at a Hamming distance of 1. Yeah?
So, this optimal k-mer size, do you think that that's more related to algorithm or?
Well, it's going to be, well, it's both. It's algorithm specific, right? What question are you asking with the k-mer? This is not in any way suggesting that MINCE should have used a 32-mer or that Quartz should have used a 16-mer. But it is also very much data specific. And I'm going to... Yeah, I'm going to talk in the last part of this. I'm going to talk about... I've got one more slide on that, but I'm going to talk a little about kind of the structure of data, and I think I will answer your question in a few minutes. I think I've got a picture that will nicely answer your question. So the other way to look at this is if we want to ensure that there's at most, so why didn't we use longer k-mers in Quartz? We want to ensure that there's at most one sequencing error per k-mer, because looking at further Hamming non-neighbors, but looking into a larger radius of Hamming distance gets exponentially more expensive. If we assume that there's an independence of errors, then for some error rate p under a binomial distribution, the likelihood of having L errors ends up something like this. At a 1% error rate, 30 tumors are 2% likely to have 2 or more errors, but 60 formers are 13% likely to have 2 or more errors. And at a 2% error rate, 30 tumors are 13% likely to have 2 or more errors, but 60 formers are more than a third likely to have 2 or more errors. So if we want to try to reduce the chances that we have more than one sequencing error, 30 tumors makes sense for this sort of neighbor investigation. All right, I want to change gears for the last part of this and talk about compression for speed. I already showed you this picture. But usually we think of compression as a space-time trade-off. Yes?
Sorry, one question about Quartz. So I wonder if all the reads that do not map, I mean, that they are not at distant ones of any part of the genome, do you keep all the quality scores?
If a read doesn't map anywhere in the genome, yeah, those quality scores are preserved. Yeah, because we don't know what to say about them. Yeah. Okay. So usually we think of,
but we should iterate on this.
Yeah.
And obviously, you know the question that I'm going to ask. What happens to multi-mapping reads? How can you?
Yeah. Yeah. So if you have for the purposes of Quartz, where the mapping. So yes, you can have a read that maps well to multiple loci. What do you do if, for example, one of those loci says you should throw away these quality scores and the other one says you should not? It's the conservative answer, don't throw them away. But there has to be some cutoff because you could have reads that map well to many loci without a significant difference in mapping quality. And I actually would have to check with William about how that's handled, kind of where is the boundary drawn and why.
It has to be all theory.
Yeah. Yeah.
One thought, you think the thing that when you do lossy compression, sometimes you actually improve over the lossless case. Mm-hmm. It's fault maybe of the sequencing masking because of the noise, or maybe it's because the variant calling algorithms are not using the quality score as they should.
It could be either. Could be both. I think for Illumina reads, my sense is that, and I'm not an expert on the sequencing equipment itself, my sense is that they have a pretty good handle on their error model. I'm not convinced that's as true for some of the more recent next-gen sequencing systems. But for Illumina reads, that's my sense. As far as the downstream calling, there's some work not yet published that suggests that there are some real problems with some of the base calling approaches and sensitivity to ordering of reads and so on. And this, it's possible that you were seeing an artifact of that, of non-determinism in base calling. Yeah, there are a bunch of possibilities. Yeah.
Do you also keep read ID?
In the quality score compression? Like for Quartz? Yeah. All of these would preserve the read name or read ID. You need to be able to reconstruct that. Yeah. There are some approaches that do some transformations on that. As I mentioned, tokenizing the read name so that it's more efficiently compressed, but that's still lossless. The only thing that any of these approaches are discarding information on would be the quality values themselves. Okay. All right, so changing gears, I want to talk a little bit about compressive genomics. So normally we think of compression as a space-time trade-off. It takes time to compress anything. It's now in a form we can't easily analyze. for many forms of analysis. So we need to then take time to decompress it. Now, maybe we only want to analyze a little part, so we only need to decompress that little part, but it's still a space-time trade-off, just a difference in how much. And what I want to talk about is some work from our lab on how we can actually use compression to speed up analysis. So Paul Rouleau, Michael Boehm, and Bonnie Berger came out with what they termed compressive genomics in 2012 with the paper of that title. K-blast, which is compressively accelerated blast. And we then had a protein version. So that was for nucleotide blast and BLAT search. We had a protein variant of this at ISMB in 2013. And the key to both of these is that BLAST uses a seed and extend approach, right? We find short k-mers, use them as a heuristic to try to extend an alignment. And the problem is, a lot of times, BLAST has to try to extend on seeds that don't lead anywhere. So what both of these did is use compression to reduce the search space. So I want to walk through how the K-blast, or specifically K-blast-P compression works. And you're going to find it's actually not too different from Lempel-Ziv, with one important difference. So we're going to initialize something called a course database. And this is going to be the thing that we're actually going to be able to search easily. And we get some sequence we want to compress. Now, initially, the database is empty. So we're going to put our first sequence into the database. And what we're going to do is index it. So every k-mer, and here I've got k equal to 4. We wouldn't actually use 4 necessarily. We actually use 6 for an amino acid alphabet. We use more like 10 or 12 for a nucleotide alphabet. But we initialize a complete seed table with every k-mer we see in here. And another sequence comes along, and the seed table contains pointers back to the location of the k-mer in here. Another sequence comes along. Well, what we do is we slide a k-mer window along it, and we see if we've seen that k-mer before. Well, we haven't seen LQST. We haven't seen QSTA. But we have seen STAQ. Rather conveniently, it's right at the beginning of this other sequence. And so we try to extend, just like BLAST would. First, we do an ungapped extension. We just greedily try to add characters until we run into a mismatch. The D and the Q do not match. And then we try a gapped extension. So here, we find that if we do a sequence alignment of these two, they match with a couple of differences. And those differences we can store. So up to here, we could, and this match can't continue here because there's no more sequence here. Or maybe there's sequence that doesn't match at all. So we can completely reconstruct this sequence thus far by the pointer by a pointer back to here and encoding these couple of differences, the LQ at the beginning here, QR, and VN. So, as I said, this is like Lempel-Ziv, except here we're allowing differences and storing them according to a couple of parameters. This part of sequence doesn't match anything, so it again goes into the course database. So, as I mentioned, this is lossless compression. We can recover the original. But what's important is we've got this course database, which has what turn out to be the unique exemplars of our original set of sequences. So the specific parameters for compression, for protein sequences, we allow, we require 70% sequence identity. They must be at least 40 residues for a match, and so on. Those parameters are all in the ISMB paper. How do we actually use this to do a search? Well, we've got some query sequence, and we've got that course database I mentioned. Well, we first do a coarse search, and this is just using BLAST, BLAST-P, SciBLAST, what have you. And we get some hits from that. Now, this coarse database is a strict subset of the original database that we wanted to search. So the coarse hits are a subset of the hits we would get if we searched the original database. But then we use each coarse hit and reconstruct all the candidates from the original database. Again, this was lossy compression, so we can reverse it. And we get some candidate hits, some maybe hits. And this search was done with a pretty loose threshold on what counts as a hit. We search this set of candidates again. We call this fine search. Here we're using BLAST again, but with the parameters the user would want for a threshold, and we get some set of results. Now, on a simulated data set where we multiplied with mutation a yeast genome, standard BLAST-P takes, as you would expect, roughly linear time in the size of the database. I think this inflection point is actually a cache artifact. And the compressively accelerated version gets much closer to almost looking like constant time over as the data set grows. Now, this was simulated data. If we look at real data growth on a protein sequence database, NCBI is non-redundant database, again, these are just 3 snapshots because you can't go back and get historical versions of that easily. This is the time taken for BLAST, and this is the time taken for compressively accelerated BLAST. We've also applied this to metagenomics, and it's really a similar problem, except given reads from a microbiome, these are nucleotide reads, we want to translate each one and match them to a protein data set. So each read is turned into a set of possible reading frames and searched against a protein database. There are several tools for this. The standard tool for this was, until very recently, still BLASTX. RapSearch2 and Diamond are much more recent approaches, and we basically applied this same compressive acceleration using Diamond to get pretty significant speed gains for metagenomic mapping with minimal loss of accuracy. So the key idea here, actually, though, is that compression is clustering. Now, when we compress data, we want to cluster similar entities or subentities. Right? These don't have to be entire sequences. They don't have to be entire reads. We're looking for similarity. But there is a relationship between compression and clustering. So with compression, we only want to store the common parts once. And with compressive acceleration, we want to only analyze the common parts once. So let me show you a picture of kind of how this works. So in compressive genomics, we do a cluster-based search. We have some cluster centers, and those partition space in some way. So the cluster centers are just the coarse sequences from that coarse database I showed you. From the point of view of a query, which is that little green guy there, we can search over just the cluster centers with some permissive radius. This is coarse search. And identify the clusters that they belong to. So we hit these 3 cluster centers. We need to look inside these 3 clusters. And we can search those clusters with the smaller radius that the user actually wants. Now, why can we get away with this? Well, due to the triangle inequality. So suppose we have clusters with some radius r sub c. And for any similarity search query, for any point within a distance r of that query, since it's in a cluster whose center is at most r sub c away, by the triangle inequality, that cluster center can't be more than r plus r sub c away from our query. So we only need to search the clusters that have centers within that distance, r plus r sub c of the query. Now, big caveat here is that not all distance functions obey the triangle inequality. And in fact, many of the natural ones we want on string data do not obey the triangle inequality. So there's a little bit of potential loss of recall. But it turns out that this is rare and tends to be on the boundaries of the search thresholds wanted. So,
more importantly, they are near metrics.
Yeah, well, that's exactly right. So they are near metrics or approximate metrics, and we expect that if the triangle inequality is almost always in practice observed, even for something that's not a metric, then we will almost always find the hits that we want. Now, some things are really bad metrics, and unfortunately, if we're talking about BLAST, the threshold input is e-value, which doesn't really approach being a metric. But it turns out that in practice, if we loosen the coarse search e-value, we still get virtually all the hits. All right. So I want to talk a little bit about next-gen sequencing analysis and how this applies. I think we have about 10 minutes. What? Oh, yeah? I mean, how are we? Okay. All right.
Can I ask a
Yeah.
question before you move on?
Sure, sure.
So for the previous example in the Quartz database, in the example you gave it looks like you're searching each representative sequence.
You would.
But in the beehive kind of hexagonal example, it looks like you're just searching the neighbor.
Let me back up.
Yeah, how do you?
The initial search, all right? So we've got, the red ones are the course examples. Those are the entries in the course database. That's just the partitioning. We're going to search all of them to find the ones that are within this radius. Okay, because we don't have a...
do search all.
Yes. So the important thing I didn't say is that although I've put these in some imaginary coordinate system, we don't have a coordinate system. So we actually, to find the ones within this ball, we do have to consider every one. The idea is that the number of these should be far less than the number of entries in the full database.
How much?
I'll get there. That's what I'm covering right at the end. And I think in the interest of time, I'm actually going to skip the variant calling stuff because you asked that question. Let me just skip over this. Other than to say we've essentially applied this to read mapping as well in a paper that was just accepted, and both best mapping and all mapping also lend themselves to this. And because you can cluster reads as well as entries in a reference genome, you get pretty significant gains. Again, this is essentially the same picture because it's virtually the same idea, except that here you've got a bipartition because you're clustering both sides of the, well, because you've got a bipartition, and you're doing clustering on both sides, you've got gains on both sides of it. Let's see. So applied to read mapping, this gets pretty significant runtime gains over Bowtie 2 and BWA, and even over Mrs. Fast Ultra when we're talking about all mapping. So, all right. Coming back to the, yeah.
I can ask one thing. I just totally forgot. Is there some cache obliviousness going on in the way you perform these searches? Built into it?
No, there's no cache obliviousness going on. Trying to do that might help a lot. Now, if the underlying, what this is really doing is boosting an existing search tool, and if that search tool does take advantage of cache obliviousness, right? So Mrs. Fast, obviously, as you know, is cache oblivious. I don't believe we've tried boosting Mrs. Fast itself, or we tried and it got marginal, if any, gains. But so Diamond, which I mentioned with respect to metagenomics search, does have some cache obliviousness baked in, and it still gains, although not as much as BlastX did. So, at a certain point, as you apply all of these other optimization techniques, some of the gains we can get through compression are preserved and because they're orthogonal gains, and some of the gains go away. The k-mer question of is this a property of the data? This is really so I want to talk about astronomy for a second. So this is a Hertzsprung-Russell diagram, and what this is a plot of temperature of a star versus its luminosity. And what does this have to do with genomic data? One thing, which is that all the data points in here come from a generative process that is constrained by physical law. And that's true of living genomes too. And what's interesting here is that, so these are what are called main sequence stars. The sun is one of the, somewhere in here. And they are constrained to a subspace here. But while it's a lower dimensional subspace, it's not a lot lower dimensional, right? It still spans a significant region of the Cartesian space. And there are other kinds of stars that can exist, but most of this space is not occupied. And in fact, we don't think can be occupied. Now, if we're looking at genomic data, the kind of search I talked about could be like a grid search or something like that, where you just look in regions. This only gives you constant factor gains. And I think genomic data looks very different. And this is just a cartoon. This is not a real plot of real data, partly because all the data sets we're talking about are very highly dimensional. And if we want to visualize them, as soon as we reduce dimensionality, we lose any structure. So we, for now, have to rely on cartoons. But this is sort of like imagine a tree of life where most genomes tend to be similar to a bunch of other genomes, or most protein sequences have similarities to a bunch of others. And you do get significant divergence, but that divergence isn't spread uniformly through space. It's constrained along branches that are evolutionarily feasible. So if we cluster this space, we see that we still need far fewer clusters. If we compress this space, we still need far fewer clusters than we would need to cover the entire feasible space. So why does this sort of search work, and what are the complexity bounds on it? Well, so we've got this sort of search tree where these are the coarse entries, or our cluster representatives, and these are the things they represent. So coarse search is done on this spine, and we look at some representatives, we expand them down and do a fine search on the things they represent. So the time should be on the order of coarse search and fine search time. But coarse search is k, that's the number of clusters we end up with. That's an emergent property, it's not an input property. So let's look and see if we can get any sense of what's going on with k. So metric entropy at a given distance scale is the number of balls that can fit on a shape. Now, in normal, I don't know enough about the background of people here to know if people are comfortable with fractal geometry. But fractal geometry is the idea that for some shapes, the number of balls or the number of rulers will scale more than linearly as their size shrinks. So we're going to define the metric entropy for some data set as the largest number of points in the data set such that they are row separated for some radius rho. And the Minkowski dimension is the limit as that radius goes to 0. But we're actually doing kind of a discrete version of this. So here, we're going to say that D is the dimension that maximizes the metric entropy, maximizes the number of these balls, these clusters. We need to cover the space. So for some radius rho that is our maximum cluster radius, if we have k clusters, then k is bounded by the metric entropy of the data set. So our search is on the order of the metric entropy plus the fine search. Now, what about the fine search? Well, fine search is a search over a set F, but F is the union over a set of spheres or balls or hyperspheres around our query at the coarse search radius, r plus r sub c. They're the sets we have to consider in our fine search. Now that's a subset, just due to basic geometry, of a ball of this larger radius around the query. So the size of our fine search set, the number of things we have to consider in the fine search, is bounded by this, which is approximately this. Now, here D is the fractal dimension at the radii we're searching at. And this is just the output size. This is how many items within our database are within radius r of query q. Well, we have to consider them because we're going to output them. The idea is that doubling the search radius increases the number of hits by at most 2 to the d. So if d is high, this is bad when we have to do our fine search. But it turns out, so this is our final complexity. And we've got the coarse search here, the fine search here. Just another quick picture of this is that we've got to consider k clusters. We then have to expand them and consider this many clusters during fine search, and for each of them, we have this term. So the key here is that I think I showed you with that earlier picture that this is, in practice, much smaller than the number of points in the database, but also that the fractal dimension is quite low. So just to give a quick intuition about that, because this also relates to another question. If we consider some point here and 2 radii around it, low fractal dimension means that as we increase this radius, we don't add a huge number more points to the larger circle. Higher fractal dimension, as we see over here, would mean that we if this is 2-dimensional, quadratically increase the number of points that we'd have to consider. So I think this, why we see data that kind of behave like this in genomics is that genomics are a product of evolution and thus are constrained by natural law. So quick summary, lossless compression is bounded by Shannon. Lossy compression can go further. Clever pre-processing of reads, and we went over several examples of this, can boost standard compressors. It all comes down to the structure of the data. We want to minimize the number of bits per base if we're talking about sequence data, identify common substrings, and find correlations among quality scores. And where to go further from here? New sequencing technologies are going to change a lot of this in terms of having longer reads, as Lior discussed. If we're talking about quality scores, this is going to change the error models a lot. And existing compressors may not work so well for something like PacBio reads, where there are a lot of indels. That's longer, more error-prone reads. Different sequencing technologies will have different error models that have to be considered. And the compressive acceleration I mentioned, we've still really only looked at for search, and I'm considering read mapping as still a form of search. If you're doing alignment, you're doing search of a form. So can we get some of those benefits with a more general model? So, thanks. I think we have time for a couple questions. Yeah.
So I may have missed it. Did you say what the empirical factor dimension that you see in practice?
I didn't show it. I do have that. I think not in this deck of slides, but in practice, for metagenomic and for protein sequence data less than 2, we also looked at some non-sequence data for protein structure. Roughly 1, and for chemical graph structure, actually less than 1. So low within the search radii that we're looking at, and obviously it's dependent on the range. Yeah.
How are you calculating the fractal dimension?
Estimating it by sampling over a data set.
How stored? How stored sampling?
Yeah. So you're just looking at, take 2 radii, and we're not shrinking these to 0 because we're interested in a discrete form. How many points are in this radius? How many points are in this? What's the ratio between the radii and the number of points? Take the log. Yeah. All right. Yeah.
You quickly mentioned BAM.
Yeah.
And so what's the connection between BAM and, say, MINCE and
So BAM is a file format, right? So BAM is a binary version of SAM. So SAM stores sequences, and it also stores alignments. It also stores quality, not just the quality scores from reads, but the quality of the alignment. BAM is a binary version of that is compressed using gzip, blocked gzip, so there's random access. And so first of all, any compressor, think of BAM as a compressor, can be bolted on after something that's doing transformation of the data. So if you're talking about the quality scores, you could do Quartz style or QVZ style quantization or smoothing of those quality scores, and then run your whatever's downstream, and should gain advantage. The other thing is if reads are reordered in a clever way so that more similar reads are near one another, you can just think of this as a permutation of the original FASTQ file. You will likely get better locality of similarity between reads, and so compressor will work better. There's a caveat, which is that some SNP colors are not even deterministic with respect to the order of the reads, and I believe there's a paper coming out soon about that.
So you changed the order of the reads. The mapping was changed.
wow.
By both types.
Yeah. Which it's worrisome.
Doesn't make sense.
Well, there's a reason for it. I mean, it's. But yeah, I mean, this sort of thing throws a bit of a wrench into the works when it comes to compression, because I mean, if you're talking about a lossless compressor for read data, this shouldn't mess up downstream analysis, and if it does, there's, it's not the fault of the compressor, but the analysis tools need to be looked at. Yeah. All right. Any other questions? All right, thanks.